everyone. I am Halima Alfarra from Group 7, Scintillation Dosimetry. In this presentation, we will talk about scintillation dosimetry, types, properties, how do they work, moreover, show the advantages and limitations of scintillation dosimetry, and explain how it can be used in modern radiotherapy. Over the last decade, there has been an increased interest in scintillation dosimetry. The detection of ionizing radiation by the scintillation light produced in certain materials is one of the oldest techniques on record. The scintillation process remains one of the most useful methods available for the detection and spectroscopy of a wide assortment of radiations. So, to know more about the scintillation dosimetry, let's discover some important definitions. What's the scintillation? As it illustrated in the figure, it's the property of a material medium that when a charged particle enters, it absorbs that energy and leads to release a photon in ultraviolet or visible light range, while scintillators are materials that produce sparks or scintillations of light when ionizing radiation passes through them. There are different scintillation materials such as organic solid plastic or organic liquid hydrocarbon or inorganic crystals, noble gases, or glasses. So, what's the scintillation dosimetry? It's a process used for measuring, calculating, and assessment of the ionizing radiation dose, such as X-rays and gamma rays, which are absorbed by the human body by using the excitation effect of incident radiation on scintillation material and detecting the resulting pulses. Accurate dosimetry enabling patients to have confidence in radiotherapy and medical imaging procedures, and radiation workers to have confidence in their safety. So now let's discover the history of scintillation detection. Previously, scintillation events were detected by naked eye using a spectroscope, which was a simple microscope to observe light flashes in the scintillator, while the modern electronic scintillation counter, invented in 1944 by Sir Samuel Curran, which replaced the naked eye with the photomultiplier tube and revived the use of scintillation, which still nowadays scintillator detectors are widely used and highly reliable and conveniently available.
Next is types of scintillation dosimetry and their working principles. Types of scintillation dosimetry can be divided into two, inorganic scintillators and organic scintillators. Before that, we go to the basic principle of scintillation detector. When ionizing radiation enters the scintillator, the measurement is detected by photographic film. As you can see in the figure below, when ionizing radiation enters the scintillator, it will emit the visible light. Brightness or frequency of flashes in the scintillator can be observed by human eye. Light output is converted into voltage pulses that are processed in the same way as pulses from proportional counters, semiconductor detectors. The whole point of scintillation detectors is that we want to produce a large light output in the visible range. Because of that, scintillation detector require for multiplier tube. First, we go to the inorganic scintillators. Most of the inorganic scintillators are crystals of the alkaline metals, in particular alkaline iodides, that contain a small concentration of an impurity. The function of impurity is to increase the sensitivity of detection by scintillation detector. One of the most common used impurities is thallium, such as in sodium iodide and silicium iodide. The table below is the type of material crystal lattice that is used in inorganic scintillation dosimetry. If you observe from the table, for every material in the bracket is the impurities such as thallium, europium, and sodium. There are also several types of inorganic scintillator that does not require for the impurities such as bismuth, germanium oxide, and cadmium tungstate. Now we go to the inorganic scintillators working principle. The scintillation mechanism depends on the structure of the crystal lattice. In a pure inorganic crystal lattice such as sodium iodide, electrons are only allowed to occupy selected energy bands. The forbidden band or band gap is the range of energies in which electrons can never be found in the pure crystal. In the pure crystal, absorption of energy can elevate electrons from the valence band to the conduction band, leaving a gap in the valence band. However, the return of an electron to the valence band with the emission of a photon is an inefficient process. To overcome that, small amounts of impurities are therefore added to the crystal. The impurities are called as activators. They create special sites in the lattice at which the band gap structure, the energy structure is modified. The energy structure of the overall crystal is not changed, just the energy structure at the activator sites. Energy states are created within what would be the forbidden band in the pure crystal. The electron can be excited through these levels back to the valence band. As we can see in the figure 1, the energy levels created by the activators present within the crystal are narrower than in the pure crystal. Then, a charged particle such as a photoelectron passing through the crystal will create a large number of electron-hole pairs. Below is the energy band structure of an inorganic scintillator. Now we look at figure A. The positive hole quickly drifts to the location of an activator site and the site is ionized. The activator sites are preferentially ionized because the ionization energy of the activator is less than a typical lattice site. The electron elevated to the conduction band is free to migrate through the crystal and will do so until it encounters an ionized activation site. The electron drops into the impurity site, creates a neutral impurity configuration with its own set of excited states. Later, the excited configuration will go to the ground state. The de-excitation occurs quickly with a high probability of photon emission. The activator is chosen so that the photon is visible. The typical half-life of the activated excited states are 10 to the power of -7 seconds, with the migration of the electron through the crystal taking a much shorter time. The timing of the light output is therefore dependent on the half-life of the state. Secondly is organic scintillators. Organic scintillators belong to the class of aromatic compounds. They consist of planar molecules made up of benzenoid rings. There are many organic scintillator compounds that can be found, as you can see in the table below. Now we go to the organic scintillator working principle. The fluorescent mechanism in organic materials arises from transitions in the energy levels of a single molecule, and therefore the fluorescence can be observed independently of the physical state. For example, anthracene is observed to fluoresce as a polycrystalline material, a vapor, part of a mixed solution. Practically, organic scintillators are organic molecules which have symmetric properties associated with the electron structure. By looking at the figure, now we go to the organic scintillation mechanism. Energy from a charged particle is absorbed and excites the electron into a variety of excited states. The singlet states, spin equal to 0, are labeled as S1, S2, S3 as in the figure. For organic scintillators, the spacing between S0 and S1 is 3 to 4 electron volt. The spacing between the upper states is much smaller. Each of the S levels is subdivided into a series of levels with much finer structure corresponding to the vibrational states of the molecule. The typical spacing is 0.15 electron volt. The second subscript denotes the fine structure level. Spacing between S states is 3 to 4 electron volt. Spacing in vibrational structure is 0.15 electron volt. At room temperature, average energy is approximately 0.025 electron volt, so all molecules are in the SOOO state. When the charged particle passes through, kinetic energy is absorbed by the molecules and electrons are excited to the upper levels. The higher states of S2 and S3 they excite quickly in picoseconds to S1 state through radiationless transitions, which is internal conversion. States such as S11 and S12 that have extra vibrational energy and are not in thermal equilibrium with neighboring molecules quickly lost energy. After a negligibly short time, a population of excited molecules in S10 state is produced as the net effect of the excitation process. That's all for the organic scintillator working principle.
Okay, next I will talk about the dosimetry properties. There are several properties in the scintillation dosimetry. Each component in the scintillation detector has properties that can affect the overall performance of the detector. First properties is the light yield. Light yield is the most important parameter because we use scintillation material. Light yield usually is measured in number of photons per megaelectronvolt of absorbed radiation. High light yield enables the detector to detect radiation of low energy with a high signal-to-noise ratio. The light yield depends on 4 factors. First is the scintillation material, second is the type of the incident particle, third is the energy of particles, and the fourth is the temperature. As you can see from the figure, various type of material and also at different energy give different value of light output. The second one is the scintillation efficiency. Scintillation efficiency is the efficiency which the energy lost by the incident particle is converted into scintillation photon. Scintillation efficiency is described as a ratio of the total energy of scintillation photons to the total energy deposited by the incident radiation. The light output is directly related to the scintillation efficiency. Most scintillator efficiency is quite poor, about few percent to 30%, but even with such low efficiency, scintillator still can be very effectively used for measurement because the light output is sufficiently high enough to obtain a good signal to noise ratio. The third is the time decay. The decay time of typical scintillation pulse is usually low, around a few nanoseconds to several milliseconds. The decay time of a pulse depends not only on the material but also on the type and the energy of the incident particle. Slow decay times in scintillators can decrease the overall efficiency of the detector. The fourth property is the temperature. The temperature is one of the important factors that affecting the light yield, as I mentioned before. This is because the charge pair yield at the material changes with temperature. As shown in the figure, the light output is decreased with increase in temperature. The decrease in light output due to temperature increase, we call it as a thermal quenching. Okay, the next properties is the density and atomic weight. Density and atomic weight of the scintillation material is one of the factors that used to determine the effectiveness of the material. Efficient detection of ionizing radiation depends on how well and how quickly they lose energy in the medium, and these are characterized by the stopping power of the scintillation material. The next properties is the mechanical properties and stability. The mechanical stability of the scintillators is one of the important parameter in detection system. Let's say, for example, because of the moisture and temperature fluctuation, the optical properties of the scintillator will deteriorate, and change in pressure also could cause cracks. Hence, if the scintillator is not mechanically stable, the detector is not well performed. The next one is the optical properties. The important parameter in optical properties is the refractive index of the material for the wavelength of light emitted by the scintillation material. Photons produced by the scintillator must be able to travel through the material without significant attenuation. Attenuation of photons can cause loss of information. Hence, longer attenuation length will increase their lifetime in the material, thus increase the detector's efficiency. Okay, the next properties is the phosphorescence, or we call it afterglow. Scintillation material produce not only prompt light but also delayed light. Delayed light is emitted because of the transition of the electrons that trap in the long-lived energy state. The cause of the afterglow is due to the slow transition of electrons that trap in the impurity levels. The longer it takes to decay, the more afterglow of the material will appear. Okay, the last properties is the radiation damage. Scintillators that usually used in high radiation field prone to damage due to the high instantaneous and integrated radiation doses. Monitoring the degradation of the detector response over time is a standard practice in such environment. Therefore, radiation-hard material are preferred over conventional one in application involving high radiation fields such as plastic scintillator, because plastic scintillator are highly prone to radiation damage. Okay. Overall, the ideal dosimetric properties for scintillation dosimetry are: the detector efficiency should be high for the incident radiation. Second, the conversion of radiation into light, or we call it the light yield, should be proportional to the energy deposited. The third one is the scintillator should have high stopping power that depend on the effective atomic number. The fourth one is the decay time should be short. The fifth one, the light output should be similar to the photomultiplier tube sensitivity. And the last one is the scintillator should be both easy available and also inexpensive.
Thus, determination in the scintillation dosimeters is based on the scintillation of light and the multiplication of electrons inside the photomultiplier tube. First, let's have a close look at the component of the dosimeter. The first component is the scintillator. The second component is the photomultiplier tube, which consists of the photocathode, diodes, and anode. This photomultiplier tube is attached to the high voltage supplier and the voltage divider. The last component is the signal reader. So when the radiation passes through the scintillation materials, photons are emitted. Then the photons are directed to the photoelectrode by light guided in some dosimeters, and some dosimeters doesn't have the light guided, and the photons are converted into electrons through the photoelectric effect and directed to the photomultiplier tube where the electron multiplication occurs. It's important to keep the photomultiplier tube in a good vacuum to minimize the loss of the electrons. Since the photocathode have a low quantum efficiency, each electron produced is so important to be collected by the first dynode. So in the photomultiplier tube, the electron is then made to accelerate and strike the dynode, which result in the emission of more electrons called the secondary electrons. The new produced electrons are again accelerated toward another dynode, where even more electrons are produced until the electrons reach the last dynode. Each of these dynodes is kept at high potential than the preceding dynode to direct and accelerate the electrons. All this potential to the dynodes and the anode are provided from the single high voltage supplier through a voltage divider circuit. This procedure of the electron multiplication can be seen in this short video. As you can see here, this is the photomultiplier tube, and this is the electron coming from the photocathode. This electron strikes the first dynode, emitting the secondary electron. Then these two electrons move to the second dynode, emitting more electrons. The photomultiplication process continues by emitting more electrons until these electrons reach the anode. After the electron multiplication process, these multiplied electrons are collected by the anode, which is located near to the last dynode. The last step is the signal readout. The output current as the anode of the photomultiplier tube can be directly measured by a current measuring device. However, the more convenient and generally used method is to convert this current into voltage and then amplify this voltage to achieve a good signal to noise ratio. The current to voltage conversion requires the addition of the load resistance to the circuit. And that's how the dose is detected in the scintillation dosimeters. Due to the good properties of the scintillation dosimeters, as mentioned previously, they are involved in many clinical and practical applications. One of these applications is the radiation measurement and monitoring. For radiation measurement and monitoring, several types of scintillation dosimeters are used depending on the application. For example, the handheld radiation survey meter is used to measure the radiation of the environment in hospitals and industries dealing with radiation. The second type is the personal radiation monitoring, which is used by the personnel working with the radiation. These dosimeters count how much dose they receive. Another type is the radiation portal monitors, which is used to scan the vehicles for security purposes in case if they are carrying or having a radioactive weapons. Secondly, the scintillation counters are used in the laboratory and research fields to count the gamma, beta, and alpha decays. The scintillation counter mainly consists of the scintillator film and the photomultiplier tube. They measure the count of radioactive decay per second, and then they display the counts in form of spectrum, as shown in the image. Scintillation dosimeters also play an important role in the clinical field, such as in vivo measurements. In vivo dosimetry plays an important role in radiotherapy safety as a final check at the end of the radiotherapy chain. Scintillation dosimeters are involved in both internal and external beam radiotherapy. In external beam radiotherapy, scintillation dosimeters are involved in treatment planning to measure the depth dose to verify the treatment at the point of delivery. Thus, detecting any errors that passes the undetected through the barrier safety checks are introduced after the final pre-treatment safety check. As you can see in the image, the dosimeter is inserted in the water phantom to measure the depth dose. Similarly, in the internal beam radiotherapy, also called the brachytherapy, scintillation dosimeters are attached directly to the skin or introduced into the patient body cavities via applicators designed to conform to the shape of the body cavity for consistent positioning, as shown in this image. These dosimeters give a real-time readout of dose to the patient, which considered an advantage of using the scintillation dosimeter.
Now, let's talk about the advantages and disadvantages of scintillation dosimetry. Scintillation dosimetry has a unique set of advantages. They can be used in situations where high spatial resolution is required. For example, plastic scintillation dosimeters show excellent spatial resolution. Water equivalence. The composition of scintillators is approximately equivalent to water, which makes them suitable for random measurement in clinical dosimetry. Also, they are independent of dose rate and can be used from 10 mg per minute to about 10 gray per minute used in external beam dosimetry. The linear energy response of scintillator dosimeter makes them highly suitable for use in radiation therapy application. Also, the temperature stability for plastic scintillators show high temperature with respect to the change in temperature, so it doesn't require a cooling system while using it. Another properties for scintillator is good isotropy and large dynamic range, which makes them suitable for use in diverse radiation environments. Finally, small size. Typical dimensions of scintillator dosimeters, which makes them suitable for medical dosimeters for brachytherapy applications. Perhaps one of the biggest disadvantages of scintillator dosimeters is that they are highly susceptible to background Cherenkov light. This can be overcome by using background subtraction counter, which requires another set of fibers and multiplier tube. Another disadvantage is radiation damage, which is defined as the changes in scintillation characteristic caused by prolonged exposure to intense radiation. This manifests itself by a decrease of the optical transmission of a crystal, which causes a decrease in pulse height and deterioration of the energy resolution of the detector. A disadvantage of some inorganic crystal as sodium iodide is their hygroscopic, a property which requires them to be housed in airtight container to protect them from moisture. Sodium iodide has no beta or alpha response and poor low energy gamma response. And finally, liquid scintillators are relatively cumbersome, which means that the detector is too heavy and therefore difficult to use. To sum up, several types of scintillation detectors have been developed in the last 15 years. Scintillation dosimeters poses a unique set of advantages like water equivalence, linear dose response, energy and temperature independence, spatial resolution. Scintillation dosimetry will be increasingly used in radiotherapy. The main applications of scintillation dosimetry, like conventional external beam radiation therapy for photons and electrons, and a quality assurance device, daily and intensely modulated radiotherapy, and it also used in radiosurgery and brachytherapy. Their advantages make them ideal for measuring complex dose distribution as those produced by intensity modulated radiotherapy. Emerging developments in plastic scintillation detectors open the door to a new era of dosimetry solutions for fast, accurate, and robust dose measurement, supporting mainstream to specialized research programs involving radiation. They can compete with other dosimeters in terms of measurement accuracy, convenience, and can be economical. So that was all we wanted to share with you. Thank you for your time.